A transversal is a line that cuts across two or more lines, and these lines are usually parallel, but they don't have to be. So for example, line AB is the transversal to lines PQ and RT. Recall from third grade that parallel lines are a set of two or more lines in the same plane that do not intersect or touch. So here is an example of two parallel lines going diagonally up to the right. We have a set of three parallel lines that are horizontal, and we have another set of two diagonal lines going down from left to right. Corresponding angles are on the same side of the transversal and in the same location at each intersection. So if we were to label all of these angles regarding its position in relation to the transversal, we would end up getting the following. For angle 1, it is in the upper left position. Angle 2 is in the upper right position. Angle 3 is in the lower right position. And angle 8 is in the lower left position. And now if we look at angles 4 to 7, we can label them in the same way. Angle 6 is in the lower left. Angle 5 is in the lower right. Angle 4 is in the upper right. And angle 7 is in the upper left position. Notice the corresponding angles have the same exact name. Angle 1 and angle 7 are both the upper left. Angle 2 and angle 4 are both the upper right. Angles 3 and 5 are both lower right, and angle 8 and angle 6 are both lower left. So that's what corresponding angles are. They are in the same position at the intersection of the transversal. Alternate exterior angles are on the opposite sides of the transversal and on the outside of the given lines. So in this diagram, there are two pairs of alternate exterior angles. We have angle 1 and angle 8, again outside of the lines and on opposite sides of the transversal. This is on the left and this one's on the right. The other pair that go together are angle 2 and angle 7. Angle 2 is in the upper right position and 7 lower left. So they're on opposite sides of the transversal and outside of the two lines that we're dealing with. Alternate interior angles are on opposite sides of the transversal and on the inside of the given lines, or in between the two lines. So we have angle 4 and angle 5 is one set of alternate interior angles, again, opposite sides of the transversal, inside of our two lines. And then the other pair would be angle 3 and angle 6. Again, opposite sides of the transversal and inside our given lines. We have another set of special angle pairs. They're called same side interior angles. They are on the same side of the transversal and inside or in between the given lines. So in our diagram, angle 3 and angle 5 are on the same side of the transversal and inside of the other two lines. Similarly, angle 4 and 6 are on the same side of the transversal and inside or in between our given lines. There are special cases or special angle pair relationships that occur when parallel lines are cut by a transversal. The corresponding angles, so 1 and 2, 7 and 8, 3 in relation to 4, 5 in relation to 6, they are congruent, each pair. So angle 1 is congruent to angle 2, and angle 7 is congruent to angle 8. And all 4 of those are congruent to one another because 1 and 7 are vertical, and so are 2 and 8. You also have alternate interior angles that are congruent. Angle 7 and 2 are congruent to one another. Angle 5 is congruent to angle 4. The alternate exterior angles are also congruent. Angle 1 is congruent to angle 8. Angle 3 is congruent to angle 6. And then the same side interior angles are supplementary. So the measure of angle 2 plus the measure of angle 5 would add up to equal 180. Same with the measurement of angle 4 and the measurement of angle 7. They would add up to equal 180 degrees because they're supplementary. These special cases can be further explained using transformations of reflections and translations. First, let's look at reflections. If we have this line A that cuts angles 3 and 5 directly in half, and we reflect angle 1 across line A, it forms angle 7. And when angle 7 is reflected over line A, it forms angle 1. Therefore, angle 1 is congruent to angle 7 by a reflection, which also proves that vertical angles are congruent. Similarly, line B cuts angle 4 and 6 in half. And when angle 2 is reflected across line B, it forms angle 8. And if angle 8 is reflected over line B, it forms angle 2, making angle 2 and angle 8 congruent to one another. If we instead drew lines in this direction, line C cuts angles 1 and 7 in half. And when we reflect angle 3 over line C, it forms angle 5. Similarly, when angle 5 is reflected across line C, it will form angle 3. So therefore, angle 3 is congruent to angle 5. With line D, it cuts angles 2 and 8 directly in half. And when angle 4 is reflected over line D, it forms angle 6. And when angle 6 is reflected over line D, it forms angle 4, making angle 4 and angle 6 congruent to one another. Now let's look at how translations can be used to name congruent angles. First, we have line M, and it's parallel to line L. If we were to translate line M y units down, it will overlap with line L eventually, just like it shows down here. And if line M is then translated x units to the left, all of the angles that are formed by lines M and N will overlap with all the angles formed by lines L and N. This will make angle 1 congruent to angle 7, congruent to angle 2, and angle 8. It will also make angle 3 congruent to angle 5, and which is congruent to angle 4, which is congruent to angle 6. The translations also work if line L, which was originally down here in this lower part, gets translated up and to the right so that it overlaps with line M. We still get the same sets of angles that are congruent to one another. Angle 1 is congruent to angle 7, which is congruent to angle 2, which is congruent to angle 8. And angle 3 is congruent to angle 5, which is congruent to angle 4, which is congruent to angle 6.